Scedrov of University of Pennsylvania. I see. Okay. Good. Thank you.
Thank you very much. It's really wonderful to be here on this special occasion for the celebration of Sergei's 60th birthday. I've had many nice visits with Sergei here, and he came several times to Philadelphia. So it was very, very pleasant to have him here. And of course, the students that are coming out of Moscow in the old days, and now out of New York, are also very, very impressive. So it's a great thing to see at this special occasion. I must say, I haven't been to many logic meetings lately, and I think I should go to more of them if they're like this. Because I'm getting a certain buzz out of this meeting that I don't always get when I go to meetings. And maybe this buzz is also some witness of quality of showcase. Okay, so I want to talk about the work on collaborative systems. And this is something that was kind of a reaction on the work that I did in security, where there is a sort of extreme adversarial relationship between the good guys and the bad guys. And eventually I became dissatisfied with this, because that's, of course there is such a thing in the world, that we're all worried about our accounts getting stolen. But it's not the whole thing. We also collaborate in some ways, not just oppose each other. So, try to see if this kind of analysis could be done emphasizing maybe collaboration a little bit more than it is in the security literature. So for the purpose of this exercise, we're going to be in a closed room. Okay? So you can think of something that you do at your office. You have to fill out some forms to apply for grants, you know. This is done usually as a collaboration among various parties. For a grant application, you have to go to your business office, maybe repeatedly. There's a person there that collaborates with you. Eventually, you send it to the dean's office to be signed. Actually, when you think about it, there are a number of parties that have to participate in this process. So, specifically for this project, we're assuming that this room is closed. So there is no intruder that can enter the system. However, as usual, nobody trusts each other completely. So you trust the other person to do certain things, but wouldn't give you a social security number to your collaborator necessarily. So while collaborating, an agent or participant in this collaboration might not want some confidential information to be leaked. Okay, so there are several things that I could do here. Let me just see how far we get with the basics, and then maybe we'll make a decision which one of these applications to look at. So first about the formalism. This is in the familiar realm here of first-order logic. I'm going to deal with representations of states or computational configurations, which I want to take as multisets. So this is not sets, and it's not lists. It's somewhere in between. Okay, I don't care about the order, but I do care about the multiplicity. All right, so on the right-hand side, you have the running example of patients coming to a doctor's office, and the doctor may want to order some tests. These tests need to be done. So again, a collaborative situation. The tests are usually sent out to some remote location for analysis. And at the end, they want to get to the doctor, and you want to get the result. You're hoping the result is good, okay? But you're also hoping for something else. Namely, that certain critical configurations will not happen along this process, okay? For instance, that your case number hasn't been connected with your name at this remote location in the lab. Okay, so your doctor should be able to connect them, but not the lab. Okay, so there are two things that we're trying to achieve. Again, we're trying to project or come up with a way of getting from one configuration to another configuration. So in AI literature, this is called a plan. If you're proof theorists, you immediately start thinking about Jensen proofs. But unlike in the traditional case, we also want to have a negative condition satisfied. Namely, I don't just want any plan, but I want a plan that avoids critical configurations. And in the running example, the critical configurations are those that publicly link a patient's name with the ID number. Okay, so this is one version of the planning problem. Okay, so we're going to do a technical assumption, which is possible because our state representations are multi-sets, not sets. So, since I have multi-sets, I can count the number of basic conditions. And I call them facts here, but what they really are closed atomic formula. Okay, so I'm going to look only at those actions which I call balanced, and that is the actions that have the same number of facts in the preconditions as in the postconditions. If you don't gain any, you don't lose any. So what does this mean? What this means is that along a plan, which is obtained by firing balanced actions, the same number of facts is always there. So intuitively, what this means is that these participants have a bounded memory. There is some comment here about security literature, which I shall skip. Okay, the results that we had obtained some years ago, basically, that the planning problem with balanced actions is polynomial space complete, while the planning problem with not necessarily balanced actions is undecidable. So let me say a few words about the p-space complete case, and then we'll look at the possible extensions. Okay, so what is the problem? The problem is that although checking for the existence of a plan is in polynomial space, however, to write down the entire plan might require actually exponential space, because the plan might be exponentially long. Okay, so what do? So you don't write down, we don't write down the whole plan. We give a scheduling algorithm, how to get from one step to another step, which is in p-space. The exponential feature of this is, for instance, clear on the basic well-known powers of time, which I can dress up as my plan. Okay, even without having any critical configurations already, this exponential space. So you can't write it. All right. So just a few words about the idea of this proof. I'm sure Dexter covers both of these things. He's complexity growth because you can't ask. So you have to check for both things, okay? Goal reachability as well as policy compliance. Okay, so what we're going to do is we're going to have a non-deterministic algorithm. So then we use Savage's theorem to make a deterministic algorithm out of this. Number one. And number two, the wonderful fact that polynomial space is the same as co-polynomial space. And that's why the negative condition can actually be fitted there. Okay, so that's the brief story. Now let me take a little bit more detail. Okay, what are the assumptions? Already said that the actions are balanced. And now the main assumption is that there are polynomial space recognition functions for the necessary notions, namely, what is a critical configuration, what is a goal configuration, and what is a valid condition. Based on these assumptions, we use non-deterministic guessing to guess the next step, and then using the assumptions of recognition functions, we check whether this step satisfies the conditions or not. Okay. And this is as far as I will go with this proof. Okay. Now. I gave the basic talk in January at a wonderful meeting in Florida, and both Gerald and Anil were there. So now, in order to entertain them for the rest of this talk, I'm going to skip the second part and go instantly to the third part, which they haven't heard. Okay. So the abstract says there are two extensions, and I will skip first extension for the interest of time. Maybe we come back to it, but okay, so now what we're going to do is we're going to introduce time into this cycle. Why do I want to do that? If you look at the co-authors here, you see something unusual. Somebody who is identified as a senior clinical trials specialist. Right, what in the world is that? Okay. So I spent many years doing applications of formal logic and security. And as part of doing this, we were reading English language specifications of security protocols, formalized them, found very interesting mistakes that people had suggested corrections, etc. Okay. But now why stop at English specifications of protocols? There are English specifications of security protocols. There are many other English specifications of protocols in the world. Okay. Having been successful at this kind of thing once, let's try it again in a little bit different domain of specification. Okay. And so for this one, we started reading FDA regulations for clinical investigations. What are those? Before medication can be made available to the general public, it has to be tested on various levels, and at the very end, it has to be tested on humans. And there are extremely strict regulations on how this is done, and that's where we go. Okay. These are called clinical trials or clinical investigations. I'm discovering that there's a big subculture among medical people who do exactly this. And what are the key concerns? So, I mean, I would call this application safety rather than security. Okay, but of course, formally, you see that there are some of them. Okay, so the concern number one is safety of human subjects. Okay, so we want to avoid at all costs that the health of people that you're dealing with is compromised during the test. There's all kinds of safeguards for test. That's number one. And number two, you actually want to collect data. Okay, the data you collect should be conclusive. Again, without compromising the health. Okay, and now why is this collaboration? Well, there are many parties that are involved here, and they're actually specified in the federal regulations. Okay. There are pharmaceutical companies called sponsor, who are very interested in selling these drugs. There's so-called clinical research organizations, which are actually conducting these experiments and writing the protocols. There are about 4 or 5 of them in the world. Not more. And they performed these, they oversee the carrying out of these tests worldwide, not just in the US. And they're all governed by the US FDA regulations. And then there are, of course, the health institutions that actually carry out the tests. They vote people, they carry out the tests. Patients come in. So they can be big hospitals that have special departments set up just for this kind of activity. Or they could be some smaller clinics in smaller towns where the usual medical care is performed at some time, and then at some other times this kind of thing is performed, so people who are doing it are also carrying out their usual medical tasks. Okay. And then another participant in this collaboration is government regulatory agencies such as FDA, Food and Drug Administration in this country. Okay, so we went to read the regulations. They're not laws, they're listed, they're called regulations. And if you read this, thing is you will eventually find the following kind of passage. That any adverse experience associated with the use of the drug that is both serious and unexpected, etc., has to be followed up by a notification to FDA. And each notification shall be made as soon as possible, and in no event later than 15 calendar days. So they're so serious. They tell you what kind of days they want, not just any days, business days, and calendar days. 15 calendar days after the sponsor's initial receipt of the information. So something went wrong, right? And then you have to send a report. Okay, so in my collaborative system, I couldn't model this. This is not eventually or forever or something like that. It's not. It's within 15 calendar days. Okay. All right. So a challenge. So now there are procedures which are elaborated by specialists explaining how one should carry out clinical trials to collect the most conclusive data with not compromising the health of the subjects. Okay. So there are two things. One is that there is explicit time mentioned, and another one, as we shall see on the example, is they seem to, let me put it this way, they seem to involve actions that may have different outcomes. And I need to deal with that as well. So what happens if you're spotted? Or what happens if you're a small clinic in a small town and your personnel is overworked? Okay? And you're performing these tests and then you're caring for the population. Few errors treatment. And the problem is that the fines are really serious. Okay, this is the amount of money that there are these institutions who make mistakes are fine are huge. And also might be getting the newspapers, and that's very bad. So critical configuration is something really critical. Okay. All right. So we're going to put timestamps on all the atomic formulas. We had a version of this some time ago with Kanovich and Okada that had the time in there, but it wasn't flexible enough. I think this version that has timestamps on all facts, atomic formula, is motivated by the work of Garg and Fenning in Logic and Computer Science a few years ago. They used it for access control. What we're going to do is use it to formalize regulations such as so we have a predicate called time, that's a global time. And now what this action is saying is that if you're within the specified time interval, okay, you got to come and get checked within 5 days. Okay. You're a participant, you're a human subject in this clinical trial, and you have to show up. So in order to write something like this, we have two things. So first of all is the timestamps on all conditions, facts, but there is also certain arithmetical conditions that I'm going to use as conditions for firing the transition. So these are conditional actions now, which were not there in the basic. Okay. Time constraints are not only there in, let's say, medical regulations, they're also there in financial regulations. There's something called the Graham-Leach-Bliley Act, GBLA, that governs performance of the banking industry. And there the there is also explicit time in these regulations, and they're very stringent. I mean, within the US, from bank to bank, the transaction has to take place within 24 hours. And it has to be verified, and the regulatory agency there should be enough of the trade so that it can be audited, and the regulatory agency can verify that this was actually done. Okay. Now, here is a case in which we may have branching plans. Right? So far, if you think about it, we only have linear. So now here's a case which happens. Let's say again, your doctor is testing your condition, or let's say you're a participant in one of these tests, and they measure everything and anything, not just the thing that's necessarily closely related to the drug and the disease that they're trying to solve, but a general physical condition. Okay. So there are, let's say here, 3 possible outcomes for this test. Okay? Or some level is high, or some level is bad. Okay? And now if your level is bad, you may have to come back. And now we need to decide on how to deal with this. Okay. So of course, one way to do it is to just have disjunctive post-conditions, which of course is going to increase the complexity immediately. Or another version is to have, instead of one single transition with the disjunctive result, that many simpler transitions with each of these cases as the result. Okay, so this is now really almost philosophy. Okay, so which one of these to take? One is internal non-determinism, the other one is external non-determinism. And we are not decided yet. It will depend on the implementation and on what the actual cases bring out. But so far, what we are thinking about it is to use some kind of hybrid approach. Okay? Basically, to be lazy. And to just use these things, this version, the simple version, for the most prevalent cases. Okay, so don't try to anticipate all the cases, because that just will blow up complexity. At least exponential is not that good. And now for those outliers, if they happen, then we may need to actually go look into and investigate all the possibilities related to that outlier. Okay, so this is the issue of exactly how to implement this in a proof assistant or a model checker, etc. All right. So now, what about these time codes? So everything is timed. Goal configurations, initial configurations, critical configurations, etc. Okay, and then there is time constraints, which are some basic inequalities. Okay. All right. Now, what is the power of critical configurations? Think about it. I have a transition system, which is non-deterministic, and all I have with this transition system is that some things may happen. Okay? But they are asking me to model that something must happen. The thing that may happen is a safety condition. That something must happen is a liveness condition. That's crazy. How can I possibly model a liveness condition within a safety condition? It can't be done. It can be done by using critical configurations. Okay. So here is a critical configuration. Okay, so that the regulatory agency is not informed within 15 days of an unexpected event. Okay, so something has been detected, and report has been sent at time T2, but T2 turns out to be greater than T1 plus 15. Okay, so that negative condition that a plan has to avoid critical configuration in fact can be used to model liveness requirements.
And if T2 is kind of too big, it models infinity, so the fact that the port never been set by simple inequality.
So I guess this is really the crux of this application, okay, is that we can model liveness requirements in policies in the non-deterministic transition systems by using the power of critical configuration.
Bounded by this condition.
Yeah, right, in this case. Okay, so now some assumptions. You see some acronyms up there. What is this? So the basic formalism was presented this January. Association for Computing Machinery has a new interest group for health informatics. And the flagship conference of that new interest group is the newly established conference on health, the International Conference on Health Informatics. The second one was held this year, and we sent this there. It was interesting to see that completely new community. We'll see where it goes. Okay. So our assumptions is this is like really simplified. Time is discrete, so natural numbers just steps. Time constraints are very, very, very simple. Okay. Only those kinds that I showed on the slides, and if you see, I was very careful to only involve two time steps in each, not three. And the conditions are very, to just affine conditions. And why is that important? That is important because we want to use the basic principle of classical mechanics, that every law should be invariant with respect to the time translation. This is the key point that underlies the complexity result. Okay. We are dancing on the edge of disaster. Okay. If you relax this condition, that's one of those things that we were discussing yesterday. If you relax this condition a tiny little bit, okay, namely allow multiplication or some other operations in the time conditions, or if you allow three things in a time condition rather than two, immediately becomes unsettled. All right. So the actions are balanced, basic conditions still there, and also the timestamps of created facts in an action in a post-condition at the moment t are all of the very simple form t plus d, where d is some natural number. Okay. So we sent in the paper with the definition of the basic system to the health conference. And the complexity results we sent to the rewriting methodology conference, the RTA, which is going to be presented in a few days in Japan. Okay, so you are seeing this before me. So in addition to these results, we also discuss something kind of a progressing condition which brings the thing down to NP completeness class, but I don't think I will have time to discuss it here. Okay. Now, we discussed what the main challenge was in the basic case. Why is it in p space? Okay. Even though to write out the whole thing fully is exponential space. So what is the main challenge here? The main challenge is that the domain of timestamps is unbounded. This is a completely different category. Everything before, up to this point, was finite and bounded and finally presented, etc. But right now, we have to deal with this time, okay? And the bad case, and the system is idling, and the clock is ticking. That is the bad case. And we have to somehow come to grips with this case. Okay. Right, so nothing is happening, but the clock is, time is progressing. Okay, so it's unbounded. So why should it be polynomial space? You have this unbounded. Okay, and so what is the solution? We're going to have an equivalence relation based on the time differences of facts. And the basic trick behind this equivalence relation is exactly what Sergei just mentioned. Namely, that if the time differences are small, that is to say, bounded by some bound Dmax, which can be computed from the actions which are presented to the system. There are finitely many actions, therefore each one of them is going to have a number associated with the post-condition, and you just take the maximum. Okay? And now, if the time differences are bigger than that particular number, then I will just think of them as huge. That's an equivalence condition. Okay. So that is to say, that intuitively, two configurations are equivalent if they have the same facts at the same truncated time difference. So, example, suppose that this Dmax is 3, okay, and then the following configurations are equivalent. R at 3, P at 4, time at 11, Q at 12, S at 14, that's one. And the other one is R at 0, P at 1, time at 6, Q at 7, and S at 9. Why? Remember, D is 3. So the differences are the same between R and P and between Q and S. But the differences in time are bigger than 3, so I don't care if they're not the same, they're just huge. Okay, so what this leads to is the canonical form, we'll call it the delta representation. So I'm not going to think about the actual configurations, I'm going to think about their delta representations, which are now very finite. And now you have to prove the lemma that if you have two equivalence configurations and a relative time constraint, then one of them satisfies the time constraint, if and only if the other one satisfies the time constraint. So therefore, if an action is applicable to a configuration, it will also be applicable to the equivalent configuration. And then you have to check that the notion of goal configurations also is closed out to the equivalence relationship. Now, this idling case can cause problems for the bisimulation if we intend to provide with our equivalence. Okay, so now there's an extra twist to it. So this intuitive equivalence relation is not good enough. It has to be made tighter. And the way we make this tighter is by introducing the notion of future bounded. That is to say, the time difference is bounded by this Dmax. Okay, so again, suppose Dmax is equal to 3. And if you look at the following configurations, which are equivalent but not future bounded, then a time advance will lead to configurations which are not equivalent. Okay, so we need to assume not just the equivalence with respect to this simple equivalence relation, but also the future boundedness condition. And now I have to prove the lemma that actions preserve future boundedness of configurations. Okay, and this is because our basic restriction that the timestamps of created facts in an action at moment t are only of the simple form. Okay, so theorem. For any given time local state transition system, the equivalence relation among configurations defined above is well defined with respect to the action of the systems, including the time advances and goal and critical configurations. And therefore, any plan starting for future bounded configurations can be conceived as a plan solely over their delta representations. And now we have the simulation. Okay, so every time you have an action that leads from S1 to S2, and you have equivalent and future bounded configurations, then that same action will lead you to S2 prime, which is equivalent and future bounded with S2. And this alpha prime is basically the same action in alpha, but instantiated with the corresponding timestamps that are coming from S1 prime. And the corollary now is that time local state transition system with balanced action, we consider the planned compliance problem with a bounded number of delta representations and with respect to the number of facts in the future bounded initial configuration. And hence, we get polynomial space completeness by the same argument as we did. Okay, so this is just the beginning. We figured out some basic mathematical models. We got p-space completeness, which is pretty good. I mean, it could be better, right? In some special case, you get NP. Maybe there's even some cases that actually come from practice that are even faster than that. At least it's not exponential. But, you know, this is 21st century. At this point, you have to follow this up and do some tool development. And this is why one of our collaborators is Caroline Talcott, who is one of the gurus on the mod symbolic rewriting system. The formalism here is very carefully chosen so that it can be taken immediately by the mod rewriting system and be run. And in fact, the RTA paper goes on from this theoretical part to now discuss the experiences which we had with this prototype that we built. You are not going, when you go to a doctor's office these days, or you go to a hospital for some sort of procedure, and what they basically do, they do the same thing that we do. They sit in front of computers, okay? And the nurses walk from computer console to computer console. That's most of the time. So just adding another part into the computer console wouldn't be that much of a change. But of course, they're not going to deal with time local transition systems, so they're not going to deal with mod. It's too complicated. So before this can be really have an impact on practice, one has to talk to people who really understand human-computer interfaces. Okay. I don't see any a priori obstacle that this could be done. Okay. But the formalism has to be chosen very, very carefully. Okay. So that the nurse who is running the clinical trial can actually do that. And then, of course, the data management issue. Formally show that privacy policies are not violated, that we haven't been talking about privacy in this case, but similar considerations are there. And then how do you actually build bridges that facilitate statistical analysis of data with existing tools? When I went to this health informatics conference, the place is actually teeming, not with people who use logic or formal methods or model checking or something. The place is teeming with people who are computer scientists, but they're using computer science for the statistical analysis of English texts. The natural language analysis. And so now the challenge in that particular context is to put the two together. Okay, and that's what this book is. I think you get the idea where we're going with this. Thank you.
Seems like there's some relation to shift invariant properties of temporal logic that I've seen before someplace.
Yeah, we are looking at the possible connections there. There is a version, so this is, as I mentioned, this is not strictly speaking temporal logic because the kind of conditions that we want are very bound. We considered to some extent, and in the privacy work, there's some very good work that uses temporal logic. But since we need these explicit conditions, we felt more comfortable using this. But it doesn't mean that it can't be done. It just depends who is doing it. But it should be.
You used the dynamical systems language for 1 second during the original part. My guess is that the business of incorporating enough into this dynamical system state so that it actually preserves it preserves the constraints in the future. That is a very good point of view by itself, and has nothing to do with logical content. In other words, it's just life control theory, where you keep something in the correct domain of operation by keeping enough information about the current state, so that based on deviations from that, you can choose.
I see. So it's a natural condition.
It's utterly natural.
Yeah, we should read that literature more, because it's really not, what we're doing is not exactly the same, but it's related enough, and the kind of things that the literature provides might actually give us guidance in how to implement it.
Thank you.